We want to apply ideas of intermolecular forces to boiling point. We're going to start by comparing bromine, Br2, with iodine chloride, that's ICl over there. So if we look at the structures, bromine, they're both 2-atom molecules. Br, ICl, single bond between the atoms. 70 electrons in bromine, 70 electrons in iodine chloride. Bromine, though, is nonpolar. Those are the same atoms in a bond. So its primary interaction is going to be dispersion, whereas iodine chloride can form dipole-dipole interactions because it's polar due to being 2 different atoms. Okay, the boiling point of bromine is 58.8 degrees Celsius. The boiling point of iodine chloride is then 97.4 degrees Celsius. Otherwise, they have very similar properties, similar masses, same number of electrons, but very different bulk properties because of their very different intermolecular force. If we think about what the liquid would look like for each of these. In bromine, I have a bunch of molecules that have, potentially dispersion interactions. You can form some interactions, induced dipoles, instantaneous dipoles. In iodine chloride, there are permanent dipoles. There's a positive side and a negative side to every single molecule. And in order to boil, right, you go from a liquid to a gas, you would be breaking all of these dipole-dipole interactions between these molecules. Okay, so that's going to require a higher temperature. So the stronger the intermolecular force, the more these molecules want to be close together, so they'd want to stay in the liquid where it's more possible to remain close together. So wanting information on the boiling point of these 2 compounds comes directly from knowing the different type of intermolecular force. It's not mass of the molecule, it's not any of that kind of stuff. It's the intermolecular force that drives it. It's not the electrons, anything like that. Is it dispersion? That's weak. That means it's going to be easier to break those intermolecular forces, and it's going to be easier to boil bromine than iodine chloride. So if we want to know the relative ordering of the boiling point of similar compounds, we need to know intermolecular force. So there's a bunch of caveats on this. We're looking at predicting boiling points, but we are not looking at predicting absolute boiling points. You do not need to be able to know that bromine boils at 58.8 degrees Celsius. You also don't need to know the boiling point of bromine relative to a very different molecule. Only similar compounds. So these are very similar number of atoms, similar number of electrons, similar shapes. That's what we want to be knowing our patterns on. Similar kind of shapes, molecules, number of atoms, those ideas. And all we want to know is the relative ordering. Just the fact that this 97.4 is higher than 58.8. So I don't expect you to know what the numbers are from the structure. I do expect you to be able to know that iodine chloride is going to be greater than bromine because of the intermolecular force. And this gets back into the ideas that we introduced previously about the fact that, say, boiling is endothermic. You always have to put heat in to do that. And you have to put that heat in because you're breaking all of these intermolecular attractions. This, for example, in water is a lot of hydrogen bonds to break. In the gas phase, these molecules are all isolated. They are not forming hydrogen bonds. So the boiling point is the temperature at which there's enough energy just coming from kind of the ambient surroundings to break all of those hydrogen bonds. In the case of water or whatever the molecule is, your intermolecular force. So if you have stronger intermolecular forces, those molecules want to stay together in the liquid. And you have to have higher temperatures are required in order to overcome that sort of ambient heat to drive the motion that we would see in our gases. And so when we're looking at this, say comparing water, H2O, to H2S, those are similarly shaped molecules, similar number of atoms, and the same kind of arrangement. What we're looking at is that primary intermolecular force. What is the strongest? Water, remember, because it can do hydrogen bonding, it can also form dipole-dipole interactions. But importantly, hydrogen bonding is primary. It's dipole-dipole is primary for H2S. That's a weaker type of interaction. So as a result, you get a lower boiling point for H2S. In this case, it's a really big difference. But we're looking for that primary interaction. So, those questions we were looking at initially, like what is the ordering, solid, liquids, and gases? We can know that things that are solids have stronger intermolecular forces, probably stronger primary intermolecular forces. All right, so what about a tiebreak? We know primary intermolecular force matters, but there's kind of some other aspects. There's a lot of polar molecules. How do we determine the order on those? So it comes into a feature of what's called polarizability. So if we look at this word, polar is making things polar. And then isa means turning it into a polar, and ability, the ability to become polar. Okay, so this is the ease of distorting electrons in a molecule, right? Electrons kind of have a standard organization, whether or not that's a polar or nonpolar. How much can they leave that? Okay, so molecules that with a higher polarizability have stronger dispersion. Because if you think about higher polarizability, means those electrons are moving around more fluidly. You can get things like instantaneous dipoles relatively easily. You can get induced dipoles relatively easily. And so the more electrons there are in a molecule, the higher polarizability. So bigger molecules have stronger dispersion. Okay, so bigger molecules have more electrons, stronger dispersion. People normally use like molar mass as a stand-in for electrons, but really it's just the number of electrons. And this is just really kind of a probability thing, right? If you think about getting like an instantaneous dipole, it's kind of like a traffic jam where you have like electrons like, jamming up on one side of the molecule. Oh, there's like electrons over here. You get an extra dipole. The more electrons there are, the more likely you get a traffic jam. It's way worse traffic in Houston than in Waco. So the purpose of this is that's a tiebreaker. If you have, say, molecules with the same primary intermolecular force, larger molecules have stronger dispersion and therefore higher boiling points. So HCl, HBr, and HI, that's a hydrogen bonded to a halogen. All of those are polar. So dipole-dipole interactions are going to be the primary type of interaction, but we can predict the relative ordering of boiling points because chlorine, then to bromine, then to iodine, you are increasing the number of electrons. It's a bigger molecule. Therefore, you get a higher boiling point. So HI has a higher boiling point because there's a lot more electrons. There's what, 3 times? It's double. It's times 2 times 3 here. Is that right? Yeah, times 2 times 3 electrons. And so there's a lot more electrons. You get a lot more backups wherever it is around the bond. And one of the ways, again, you can kind of think about what goes on here is that like HI is polar, and all of a sudden it can become more polar because of a backup of the electrons, or kind of strengthening or enrichment of electrons in one side of the molecule and a depletion on the other side. And also really big that inducing dipoles is very easy, so you can really get a lot of effects from that. So this is really important in the world of nonpolar molecules, right? If we remember, nonpolar molecules only have dispersion interactions. And so if we look at, say, carbon and hydrogen, we said molecules that feature carbon and hydrogen were always nonpolar. And what that means is that they only have dispersion interactions. That also means for carbon and hydrogen containing molecules, hydrocarbons, their boiling point is determined entirely by the size of the molecule. Bigger molecules have larger boiling points. And so we look, this is kind of just a chain CH4, C2H4. You can see this table. You're just increasing the size, and we can see that it's increasing melting point. So low down C3H8, that's propane. So like a propane tank, that's a gas at room temperature. It boils at -42. And if we go down, bigger and bigger molecules, C7, H16, which is interpolated here. Heptane, that's one of the common components of gasoline. Octane is also in gasoline. We can see that those are liquids at room temperature. That makes them really useful for fuels. It's pretty easy to pump gasoline into your car. You think about all the kind of protections around pumping propane into a tank, because getting gases is a little more tricky. And so this can keep going. When you go to C31H64, that's a really big molecule, and it becomes a solid at room temperature. So that's like candle wax is C31H64. And so these hydrocarbons, these carbon-hydrogen containing compounds, we can see that even though they only have dispersion, if they get really big, there's a lot of electrons in those molecules, and you can start to drive really strong dispersion interactions that functionally lead to the formations of solids and liquids. You'll note like water with its hydrogen bonds is a liquid with, say, 3 atoms. C7H16 has like 23 atoms, and now it's forming a liquid. And so it requires this growth of molecules, this large number of molecules, in order to get to that liquid and to get to those levels of boiling points or eventually forming solids. And actually, this idea is how we refine crude oil. So when you take oil out of the ground, there's a bunch of hydrocarbons in there, and they are all, carbon and hydrogen, and there's no real chemical difference between them. They all just have carbon and hydrogen. They're doing similar types of things, and so how they are separated is through their various boiling points, through a process called distillation. So the towers you see at the plants are all, column. You will hear them referred to as columns. That's because they are doing distillation in a column. And so what you do is you do variable kind of heating. And so you can imagine there's some hydrocarbons that you heat it up to say 300 degrees, 370 I think in this one. There are some that are so big that they don't boil at 370 degrees, so they're still liquids. And then as what boils goes up the column, it starts to cool down away from the heat source, and so things become liquids at those cooler temperatures, and then they flow off. And they flow off here, and eventually you get the things that are gases or even gases at room temperature that pop out. And so, small things that are gases at room temperature, you get things like, use a lot of things like natural gas is up there. As you go down to larger and larger, you get things like heating fuels. Eventually diesel starts to come out, heavier chemicals, waxes, asphalt comes out of this, like road surfacing is asphalt. It's really, really big hydrocarbons. And so all of these kind of go on. And so, this column is an idealization. One of these columns is a pretty small temperature gradient that they're using. And that's why there's so many columns at a given plant to get really fine separation of all these different compounds. So let's look at an example where we use this idea. We're going to order our substances by increasing boiling point. So I got H2O, H2S, H2SE, and H2TE. If I want to know boiling point, whenever we're predicting the property of a bulk phase, it's going to be based on what are the intermolecular forces, what are the strengths of those intermolecular forces, and how does boiling point relate to that? So we know stronger forces leads to higher boiling point. And again, I just want relative order. I want to arrange them by increasing boiling point. I don't need numbers here. So what are the primary intermolecular forces? What are the Lewis structures? And you'll note O, S, SE, and TE are all in group 6A. So these things all have similar Lewis structures. They all have 6 valence electrons. So they need 2 more to get an octet. So they all form 2 single bonds to the hydrogen. And they have 2 lone pairs. Okay, so if I look at this, I can see water, again, we've talked about before, can form hydrogen bonds. If we look at the rest of the molecules, there are lone pairs on the central atom, which means they can all form dipole-dipole interactions. They're all polar. So we know right off the jump, we expect water is first. Water should have the highest boiling point among these. But how do we distinguish the rest of them? They're all dipole-dipole. And this is where that idea of bigger comes in. Just like with the nonpolar hydrocarbons, bigger molecules have higher boiling points here. And so these are arranged by going down the periodic table, sulfur to selenium to tellurium. Tellurium has the most electrons by far. It's a bigger size. It has stronger dispersion, so stronger interactions. So water is going to be first, then H2TE, hydrogen telluride, then hydrogen selenide, and then the hydrogen sulfide on down the line in the order that we have right there. So we can make this prediction. And this prediction that we did, you'll note we did it for group 6A, all the hydrogen compounds in 6A. But this is in general true for group 5A, which is the nitrogen column, You can see that has hydrogen bonding, and then we get this kind of, everything else is dipole-dipole, and we get the ramp up based on size, the halogens with fluorine, and water with its oxygen, with that column. And so with this, we can see that we can make these predictions. We can understand what's going on. You will note within hydrogen bonding, the rules for dispersion don't work. We would predict ammonia, but we are okay. That's okay. We're not, hydrogen bonds are kind of their own little world. We just know they're all going to be really strong. And water, particularly, you can see has very strong hydrogen bonds. That's why it's very important for water and very important for all the things that we use water for. Participation 114, question 3. Which substance has the higher boiling point? CH3F or CH3OH? This is the third question on participation 114, due Friday, January 14th at 11:55 p.m. Over on Blackboard. Link to the assignment is right below the links to these videos. Which substance has the higher boiling point, CH3F or CH3OH? Again, you just want to write out which substance has the higher boiling point over on Blackboard, CH3F or CH3OH. All right, so 3 videos. We have found 3 participation questions. I really promise it won't be in every single video. See if we can find one in the next one, though. We'll see you in the next video.